Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on August 4th, 2025, so just yesterday. Using the new framework from this paper, researchers trained a 30 billion parameter Omni-Modal model at over 2,800 tokens per second per GPU and scaled it to 160,000 context lengths. The paper is titled VeOmni, Scaling Any Modality Model Training with Model-Centric Distributed Recipe Zoo. And the implications for training these massive, complex models are pretty significant. It introduces a new approach that tackles the huge engineering challenge of training omni-modal models, which can understand things like text, images, and audio all at once. Also, the authors shared the full implementation on GitHub. If you head over there, you'll find the complete VeOmni framework, which is packed with training scripts, example configurations, and quick start guides for popular models like Llama and QN. It's a whole toolkit for scaling your own training experiments. Alright, so this figure really visualizes the core innovation. On the left, we see the old way of doing things for multimodal training, where the model's core logic for computation is all tangled up with the communication needed for parallel training. This gets really messy and inefficient. Then on the right, we see the new VeOmni framework's approach. It cleanly separates these two. You have a central computation-only module and a separate toolkit of distributed training recipes. These recipes handle all the parallelism, like fully sharded data parallel, which splits the model across GPUs to save memory. This decoupling is what makes the system so flexible and scalable. Building on that idea of decoupling, this diagram shows the plug-and-play architecture. It's made of 3 independent modules. On the left, you have the various encoders. These take in different types of data, like images or audio, and convert them into tokens. Those tokens are fed into the central foundation model, the core LLM. Then, on the right, the decoders take the processed information and generate the final output, which could be text, an image, or another modality. This whole structure is what enables that flexible, any-to-any capability. Okay, so this diagram shows how the framework pulls off this complex parallel training. On the left, you can see the computation and communication happening on separate streams, which is that key decoupling we just talked about. Then, the right side visualizes the 3D parallelism system in action across multiple GPUs. It's combining different strategies like sequence parallelism for long inputs and expert parallelism. Expert parallelism is a technique for scaling mixture of experts models, which use specialized subnetworks by distributing those experts across different devices. So, moving to the results. These charts show how well that 3D parallelism works in practice. The plots on the left measure performance for a 30 billion parameter model. As you increase the sequence length, which is the amount of data the model sees at once, you can see the trade-offs with memory and throughput, or processing speed. Then, the plot on the right confirms that the training is stable. You can see the loss, which is basically a measure of error, consistently decreasing for 3 different omni-modal models, proving the framework is effective. Alright, to get a real head-to-head comparison, the authors benchmarked their framework against Torch Titan, a state-of-the-art system. This table shows the results for a large, 32 billion parameter model. We're looking at memory, throughput, and something called memory footprint utilization, or MFU, which is a metric for how efficiently the GPU memory is being used. You can see that as the sequence length gets really long, up to 128,000 tokens, VeOmni keeps performing while Torch Titan runs out of memory. This really highlights the efficiency gains. So to wrap things up, VeOmni really addresses a critical bottleneck for training the next generation of AI. By cleanly separating a model's logic from the complexities of parallel training, it provides a robust and scalable framework for building these huge, any-to-any omni-modal models. That's it for this episode.